Greetings. We'll continue our discussion from the point that we left yesterday. What we had introduced yesterday was an operator called as the Hermitian adjoint. So, for an operator A which operates on an operand alpha, you define a dual conjugate relation, and it is this dual conjugate relation, just the definition of this dual conjugate relation led us to discover that the adjoint of the product is the product of the adjoints taken in the reverse order. So, that comes automatically from the very definition of the Hermitian adjoint. So, hermiticity is a property of those operators which are self-adjoint. If an operator is self-adjoint, if its adjoint is equal to itself, then you say that it is a Hermitian operator. It is a self-adjoint property. And for these operators, there is a very important theorem in quantum mechanics that the eigenvalues of a Hermitian operator are real, and the eigenkets of the Hermitian operator belonging to different eigenvalues are orthogonal. So, we will discuss this theorem today. So, we begin with the associative property that you have a matrix element of A between states beta and alpha, and I am already using the terminology matrix element and so on, but essentially what you see is you can factor this process as if you have an operand alpha on which the operator A operates, right. So, it is like a measurement represented by the operator A, and then you project this on the adjoint of the vector beta. And because of the associative property, you can also think of the inner product being constructed first by operating A toward the left on the adjoint of beta, okay, and then taking its inner product with the vector alpha. So, either way it works out the same because of the manner in which you can read this associative property. So, given this, we now do some simple analysis. So, you have got this matrix element beta A alpha, which is of course equal to itself, and what will make it equal to itself? I can complex conjugate it and then complex conjugate it again. So, I take the dual conjugate of this and then take its complex conjugate, and the dual conjugate of this is nothing but the dual conjugate. This part is the same, but A alpha I can interpret as a new vector which is gamma. So, the result of the to be, it is a simpler notation of A operating on alpha. You can also ask what will be the dual conjugate of gamma, and that from the definition of a adjoint operator you know is A dagger operating on alpha on its left, right. So, now you know what this dual conjugate gamma is, right. So, we can put it over here because beta A alpha is gamma beta complex conjugate, and essentially what you find from this, since this gamma is nothing but A dagger operating on alpha on its left, you find that beta A alpha is the complex conjugate of alpha A dagger beta. Now, this is going to be true for all the operators for which you can define an adjoint operator. Now, so far so good. If you have an operator which is self-adjoint, then this relation which is valid for every operator beta A alpha equal to alpha A dagger beta complex conjugate, this A dagger can be replaced by A itself for self-adjoint operators. Okay. And now let us look at these self-adjoint operators. So, let us have an eigenvalue equation for an operator omega. and let us say that you get an eigenvalue omega prime which you use to label the state vector, and that is the reason this omega prime is sitting in this ket. You can take its projection on another ket which is omega double prime, and it is a dual conjugate in the dual conjugate space, but omega double prime may or may not be equal to omega single prime. It may or it may be, it may not be. So, that is something that we will consider both the possibilities. So, you have this matrix element, and since omega prime is an eigenket of omega, it comes out over here, and then you have the inner product of omega prime with omega double prime. So, that is over here, right. So, I hope you are feeling comfortable with this notation, because when you take this inner product of this ket with the adjoint of omega double prime, it would seem as if there are two vertical lines coming in the middle, whereas over here you have only one. So, when these vertical lines in the notation come together, you can collapse them into a single one. So, you will get used to this notation as we start using this. You can take the dual conjugate of this relation, of a similar relation, but for a different eigenstate which is omega double prime, and then take its consider the fact that omega dagger is equal to omega, because we are dealing with Hermitian operators. So, for Hermitian operators omega dagger is equal to omega, and you have this relation, and you can take its projection on omega prime. So, just the way you project out a ket vector on an adjoint bra vector, you can also project out an adjoint vector which is the bra vector on a ket vector. So, that is what we have done over here. So, this is the relation that we get. Now, see what you get. I have given the equation numbers now to this. So, I call this as equation 1, and this is equation 1 prime, and this is an equation 2, and this is equation 2 prime. So, it is going to be a little easy for us to discuss these terms by numbering them, and I will carry these equations 1, 1 prime, 2 and 2 prime to the next slide. Okay. So, you have got equation 1 here, 1 prime here, and 2 prime here, and all we do is to subtract equation 2 prime from equation 1 prime. Now, when you do that, the left hand side's equation 2 prime has got this left hand side, and left hand side is the same. So, the left hand sides cancel each other, which means that the product of these two terms goes to 0. So, if one of them is 0, then only the other may be non-zero. So, that is the conclusion you can arrive at. So, now it is very simple, because omega prime is either equal to omega double prime, and if that is the case, then the inner product of omega prime with its adjoint vector we know is not 0, because this is what will give you the norm, right. So, this will not be 0, and it means that the other factor will have to be 0, and you can conclude that omega prime will have to be equal to omega prime complex conjugated. If you consider the other possibility, you will find that it is this inner product which must vanish, which is a statement of orthogonality. So, it is either one or the other, and that leads us to the conclusion that if omega prime is equal to the complex conjugate of this, it means that the eigenvalues of the Hermitian operator are real, and then also that the eigenkets of the Hermitian operator belonging to different eigenvalues, when omega prime and omega double prime are different, then these must be orthogonal, because they have no component on each other. If you take the projection of one on the other, that goes to 0 for orthogonal vectors, right. So, this establishes an important theorem, and this will remind you of the vectors you work with in 3-dimensional Euclidean space R3. So, it is very similar algebra, and you can think of a basis set which has got not just 3 dimensions, but perhaps even more, 1, 2, 3, and I represent these extra dimensions by these dots, and for comparison I consider 3 orthonormal unit vectors in the Euclidean R3. Okay. So, you have these unit vectors which are linearly independent. I also consider them to be orthogonal to each other. You can always orthogonalize a basis using some sort of a Gram-Schmidt orthogonalization. Okay. So, you can expand an arbitrary vector, an arbitrary position vector is a superposition of the unit vectors E1, E2, E3, where these are the 3 unit vectors along the 3 orthogonal directions in the Euclidean R3. So, here you have got a very similar relation, that an arbitrary vector is expressed as a linear superposition of the base vectors. So, these are the base vectors AI. How do you get the projection of any vector along any one direction? If you want the projection of component of R along the x axis, you will just, all you will do is to take the projection of R along that unit vector. So, you will construct the inner product, you will construct the scalar product, right, and this is just what you do over here as well. You take the scalar product or the inner product, which is the projection of alpha along the base vector Aj, and that will give you the component Cj. It is coming from this orthonormality, because the inner product of Ai with Aj will be a delta Ji, just like the inner product of a Ei with Ej is delta Ij in the 3-dimensional basis set. Okay. So, you have a very analogous situation, right, and you can use this analogy to your comfort, but you still have to be a little bit careful, because I like to warn you that you should use the strengths of the analogies, but you should also be aware of the limitations of the analogies. Okay. The limitation of the analogy comes from the fact that this inner product Ej dot Ei is exactly equal to Ei dot Ej, whereas the inner product of alpha with beta in the Hilbert space is the complex conjugate. So, if you swap the indices, you get complex conjugation. That does not happen in the 3-dimensional Euclid's space. So, in other words, the 3-dimensional Euclidean space R3 that we normally work with, okay, it has got a dual conjugate space, which is itself. Okay. It is its own dual conjugate space, but that is in general not true for vector spaces which we use to represent the physical states of systems. So, that is the difference. Okay. Then let us continue to use the analogy, because as long as it is useful, I am sure we can draw some mileage out of it. So, you have these coefficients in ordinary, so this will be the x component if this is the unit vector Ex, this would be the y component if this is the unit vector along the y axis, and so on, right. And the components are given by the projection of the vector along the unit vector. So, you have exactly the same situation as we discussed on the previous slide as well, right. And you can, having extracted the component, we can write this component in the Dirac notation, in the bracket notation, instead of as a complex number Cj, which is what I have done over here. And then I recognize that what I have over here is the component, and I have this vector here, but it does not matter if I write this vector first and this complex number after it. Okay? And look at how the notation is evolving, because now this curved bracket is really not necessary. I already have this Dirac bracket, and there is no need to put it in another curved bracket. So, we remove it, and now what you recognize is that the vector R is equal to this particular term, which is like this effective operator operating on the ket R, which leaves it invariant. In other words, you have discovered the resolution of the unit operator. So, this is the unit operator in ordinary 3-dimensional space, and there is a corresponding unit operator which you can get for vectors in the Hilbert space. Once you have the basis set, it will come out exactly doing the same kind of algebra. You get the component of alpha along a base vector times the base vector, and when you superpose all of these, I must go from 1 through whatever is the dimensionality of that Hilbert space, and then you can rewrite this bracket before this vector or after it just does not matter, and what pops out of this is the resolution of unity in the Hilbert space. So, this is an operator, and yesterday we discussed that you have different kinds of products. You have got inner products which are complex numbers, and you have outer products which are operators. So, this is an outer product. The bracket is a complex number, it is a scalar. This is the ket bra, but it is a sum over all of I, and summing over the complete dimensionality of the Hilbert space is absolutely important. Without that, it would not be a unit operator, because unless you add up the projections on all the unit vectors, you will not be able to recover an arbitrary state vector. You may get some special components, okay, if you have a vector which is got a direction, which has got a projection only along the x axis, you certainly do not need the y and z components, but an arbitrary vector requires all the components. So, you must sum over the entire space, and that is the importance of what is called as completeness. This basis set must be complete. What it means is that an arbitrary vector should be expressible as a superposition of all the base vectors. In that case, it is complete. Okay. It also gives you a sense of closure, because when what is happening is that any arbitrary vector, it is not when you construct this linear superposition, it is not thrown out of the space, it remains within the same space. Okay. So, this is the resolution of unity. So, you have got completeness, you have got closure, this is called as the identity operator, and you can write this identity operator ket bra ai, write it in a different notation. I have used this lambda I to represent that. And what is lambda I doing? Lambda I is projecting out of the net vector of an arbitrary vector alpha the component which alpha has along the ith base vector. So, it is literally picking the component, and that component since it is picked by lambda, just the ket bra ai is a projection operator for the ith state. Okay. So, it is picking out the component which is along the ai vector. What is the value of that component? It is this. Okay. This is the value of the component. It is the projection of the vector alpha along the unit vector ai. So, it is just like taking the shadow of a vector along any base vector in ordinary 3-dimensional space. So, now we know that if you sum over all the projection operators, you get the unit operator. Right. So, now what we will do is to use a representation, and this is a representation theory. The fundamental theory of quantum mechanics is in terms of the vectors using matrices. So, what is the big information in a vector? Any position vector in ordinary space is completely specified if you give its components x, y, z. So, given an orthonormal basis, if I say that okay, the components are x and y and z, you get complete information about the system, right. So, the information is really sitting in the components, which will be different for different vectors. So, I can represent this vector by these components. How many components are there? As many as the dimensionality of the space. So, I stack all of these components in a column, one below the other, and I have got these n rows, and this looks like a matrix to me. It is a column matrix, and this has got all the information that is necessary to spell out the arbitrary vector alpha, because the information about the arbitrary vector alpha is contained in its components. So, this is the matrix which represents the state alpha. So, a vector is denoted by a column matrix, because it has got all the information that is required. So, this is an arbitrary state alpha. It is represented by this column matrix. We consider another vector beta. This is a different vector, and therefore, it will have components which are different, and it will be represented by a different column matrix. Now, I consider the adjoint of this vector beta. So, this is the adjoint of the vector beta. Okay. So, I have just constructed the adjoint of the superposition, which will be a superposition of the base vectors in the dual conjugate space scaled by appropriate coefficients, which will be the dual conjugate of these coefficients. Okay. So, it comes very neatly as this, and now all the information about this adjoint vector is contained in these transformed matrix, first n rows and 1 column. Okay. So, I represent the vectors in the direct space as column matrices and vectors in the adjoint space by the row matrices. What this enables me to do is to use matrix algebra to mimic the algebra of the vectors in the Hilbert space, and since it mimics one to one, I say that I have got a representation. So, this is the matrix representation which we are now discussing. So, you have a vector in the Hilbert space which is represented by a column vector, an adjoint vector represented by a row matrix, right. And notice that this is a matrix of 1 row and n columns. This is a matrix of n rows and 1 column. So, you can actually multiply them. Okay. You can multiply the 1 by n by n by 1, and you will get a 1 by 1 number. Okay. Only a single number will pop out of it. So, which is what you expect when you take the inner product of alpha with beta, because this is just a complex number, this is a scalar. Okay. It will not have many components, it is just a complex number, and if you just write these terms as matrix multiplication, essentially you find that it is completely equivalent to sticking in a unit operator between beta and alpha, which you can always do, because a unit operator will do nothing. It is a very harmless operator. It will leave a ket invariant on its right, it will leave the joint vector invariant on its left. It is completely harmless, right. So, you essentially have this as a product of j going from 1 through n, whatever is the dimensionality, but these are of course complex conjugate terms, because we have defined the projection of alpha on aj as c and the complex conjugate as Cj star, right. So, you have got this complex conjugation which is indicated by this asterisk. So, this is the matrix multiplication that you have carried out. So, product of 1 by n matrix with n by 1, which gives you this scalar. So, this is an inner product, construct the outer product. So, the bra ket is an inner product which is a scalar and a complex number. The ket bra would be an outer product, and an outer product would be an operator. Okay. So, if you write alpha as a linear superposition of this, which is here. Okay. So, it is like writing the unit operator behind this alpha. You see it over here, and then you have this adjoint vector beta, and then you have this unit vector, unit operator appearing on its right, and this ket bra therefore is the column vector appears first and the row vector appears next. So, this is an n by 1 matrix with n rows and 1 column. This is 1 row and n columns, this is 1 by n. So, it is defined without any hassle, and you will get a result which is n by n. So, you will get a square matrix coming out of it, which is n by n. So, operators are represented by these n by n matrices. These are square matrices, and this is what we mean by a matrix representation of an operator. The matrix representation of an operator, you can represent operators by these square matrices, okay? And this is now you can construct this matrix multiplication, which is very straightforward. You know how to multiply matrices. You take term by term, you run your finger on one matrix left to right and the other finger on the other matrix from top to bottom, take the terms and then add up all the pieces, right. So, when you add up all the pieces, you are able to get the every term in the product matrix, and the products over here are essentially, this is the projection of alpha on the base vector A1. So, it is alpha 1, and this is the complex conjugate of the projection of beta on A1. So, this is beta 1 star. So, these are the matrix elements which represent the operator. So, this is the matrix representation of an operator A. You can think of it like I said earlier, as if you have sandwiched the A operator in between two unit operators, and you get exactly the algebra that we just carried out. Okay? So, this is the algebra that we have effectively carried out. So, all the information about A is sitting in what you see in this rectangular box. Just like all the information about an arbitrary vector was sitting in those coefficients, here the signature of the matrix of the operator is sitting in this term, which is sitting in this rectangular box, of which ai can take n values, I going from 1 through n, and j can take n values, j going from 1 through n. So, there are n square elements which are the matrix elements. Okay. Each is a matrix element, it is called as a matrix element. This is a matrix element of the operator A between the states ai and aj. So, I have already used a terminology, and you have sort of accommodated that comfortably, because it comes so naturally in this system, because matrices give you excellent representations of the vector algebra. So, we do not even realize that you have moved over from the algebra of vector spaces into the matrix algebra. Okay. So, these are the n square terms which are of importance, and you can write them in a more compact notation by writing the row index and the column, the row number and the column number as subscripts. Okay. So, there is some convention that you have to come up with, and you have the row index 1 and the column index 1 over here, right. So, the row index is coming from the left side, which is from the adjoint vector, and the column 1 from the ket vector. So, an arbitrary vector is represented by this matrix element Aij. So, this is the notation which you will find in Sakurai's book also, that the operator A is represented by the matrix, and these two, because this equal to with a dot on top is the notation which Sakurai has used in his book. I tend to like these fat letters to represent matrices. Okay. So, whenever you see a fat letter, it is a matrix. Okay. That is a notation I used. I was introduced to this notation by Paralav Laudin in a summer school which I attended, and he, you know Laudin. So, Laudin always used to say that okay, use fat letters to represent matrices, because then you know what is an operator and what is a matrix. And if you start using fat letters for matrices, he said that you have become members of the fat symbol society. So, I encourage you to accept the membership of the fat symbol society. So, my wife says that I am a member of the fat society. So, anyhow, so you have got the matrix representation of an operator, okay? And now you have this relation Aij. Now, this is true for any operator, but if A dagger is equal to A, which is true only for a Hermitian operator, then you can replace this A dagger by A, and you have these relations for the general expression for the matrix element of an operator. So, in the case of all the operators, Aij is equal to the jith element complex conjugated of the corresponding Hermitian adjoint operator. If that operator is self-adjoint, it is just the complex conjugate of the operator, but with the indices interchanged. Okay? So, this is a very convenient result which holds good only for Hermitian operators. And we need to begin to like these Hermitian operators, because we just discovered earlier in today's class that they have got real eigenvalues. So, they are excellent candidates to represent operations, to represent measurements, because when you carry out a measurement, you expect a real number to come out as your answer. Okay? If you measure your mass or height or something, you do not want a complex number to come out of it, right? So, these Hermitian operators have got real eigenvalues, and for these the matrix elements have a very simple form. So, now this brings us to a very important interpretation of these coefficients which have appeared in our expansions. They attain in quantum mechanics an interpretation which is probabilistic. You need statistical mechanics, statistical considerations to interpret these coefficients. And throughout this discussion, I am reminded of Wigner's brilliant comment that mathematics lends itself as a very powerful and natural medium to express the laws of nature. It might appear to be unreasonable, but it works, and we need to gain maximum benefit out of it. Okay? Now, the probability interpretation was developed by Max Born, and it is very nicely expressed over here in this result, because we have also learned what a measurement does to the system. If you have not carried out the measurement, you will have to express the state of the system as a superposition of the unknowns. The entire basis set, the complete basis set, Completeness is mandatory, because without that you cannot express an arbitrary state. And as long as you do not know what it is, and you would know it if and only if you made a measurement. As long as you do not make a measurement, you do not know what it is. Go back to Einstein's question, is the moon there if nobody is looking at it? You have to do a measurement, look at it, and then tell me if it is there or if it is not there. Okay? As long as you do not look at it, you have no information about it. If you have not looked at it, it is in a state of it is there and it is not there. It is in an entangled state. The cat may be either dead, the result of which it will collapse into one of the eigenstates. So, measurement is fundamental to quantum mechanics, and the probability with which it will collapse into one or the other eigenstate is that information is contained in these coefficients. So, look at this statement by Dirac. What does a measurement do? A measurement always causes the system to jump into an eigenstate of the dynamical variable that is being measured, because that is just the information that you get out of that measurement. So, if you have not done the measurement, which is before the measurement, an arbitrary state vector requires a superposition of all the base vectors. But if you do the measurement, then the result will be one of these. It will no longer be a superposition state, it will be one of these, let us say the kth one, and you can ask what is the probability with which you will get it in the kth state and not in k plus 1th state or k minus 1th state or any of the other n minus 1 states. So, that probability is given by the modulus square of this coefficient. It is some sort of a weight, it is some sort of a measure. It will give you the probability, and this is why probability enters quantum mechanics, not because there are a large number of particles that you are working with. That is what you have to do in classical mechanics. There is just too much information to handle in the kinetic theory of gases, in Maxwell distribution of velocities, right. It is just too much information. So, you come up with some average properties. You say that okay, I do not want to keep track of the velocity of every molecule of the air. Let me get some estimate of the average, and I make an estimate of the average kinetic energy of all the molecules, and it is this average that I can give it some other name, which is temperature, right. Not because the individual velocities of all the molecules cannot be tracked. In principle, they can be tracked, and they will all respond to interactions, they will get accelerated by interactions, you can follow their temporal evolution using Newton's laws. It is completely deterministic, but it is just too much information, and numerically you may not be able to handle that problem, that is a different matter. But if only you could solve the mathematical equations coming from those many particles, there is nothing uncertain about that situation. But here you have intrinsic uncertainties. So, statistics enters this analysis not because you are dealing with a number of particles which is large, but because probability and statistics is inherent to quantum mechanics. So, this is the result that we get from the Born interpretation of quantum mechanics, which I use Dirac notation for this. And then we also know from the Stern-Gilrack experiment, which we discussed in the previous class, that if you carry out a measurement on a system which is already prepared in an eigenstate, and you carry out the same measurement, you will get the same result. You are guaranteed that you will get the same result. There is no uncertainty there. There is a 100% guarantee, which means that the corresponding probability is exactly equal to 1. Probability being a number between 0 and 1, this probability is exactly equal to 1 if you carry out a measurement on some system which is already prepared, if it is already in an eigenstate, and you measure that property again, you will get exactly the same result. Okay? So, the probability will be exactly 1. So, what result you will get really depends on how you have prepared the system, and this is what Heisenberg in Heisenberg words, what he says over here is that what we observe is not nature itself, but nature exposed to our method of questioning. This is a very deep comment on what reality is. What it is telling us is that reality, what we are going to call as reality, depends to some extent on how we are exploring it. Without that, reality does not have an independent existence. At a philosophical level, this is a very deep question, right? And this is part of the reason Einstein was never happy with this. And Einstein kept questioning this, he kept challenging the statistical nature of quantum mechanics, and he was saying that, okay, you do not have this complete information because some information is missing, something is missing, and if you are able to put that information back, then it will take away the probability out of quantum theory. So, he came up with many arguments and was always beaten by Niels Bohr, because Bohr found inconsistencies in Einstein's arguments. So, you can remind yourself of the Stern-Gerlach experiment once again, which we discussed early on. And like I mentioned, this really illustrates the fundamental principles in quantum mechanics in a very beautiful manner, which is why it appears toward the very beginning in the book by Sakurai. This figure is straight out of Sakurai's book, we have discussed this earlier, but I want to remind you one more time that you have got these silver atoms which you generate the z axis. Now, because of the electron spin, there are two components up and down, plus and minus, and over here it is not. It has already been prepared because you have carried out a measurement here, and having carried out that measurement, you know that the system is in an eigenstate of the z component, which is the plus component, and if you repeat this measurement, you do the same measurement, then you are guaranteed that the result will be Sz plus. This is the probability 1 in the on the previous slide. There is a 100% guarantee that you will get the same result, okay? And there will be no Sz minus component. Okay? On the other hand, if you have prepared it in an eigenstate of z, but it is not an eigenstate of x. An eigenstate of z is not an eigenstate of x, and the reason for this is deeply rooted in quantum mechanics, which comes from the properties of what we recognize as angular momentum in quantum mechanics, because the magnetic moment is coming from a quantum angular momentum whose components do not commute. So, if it is an eigenstate of z, you are guaranteed that it will not be in an eigenstate of x, and what comes out of this will be a superposition of x plus and x minus, because these two measurements are not compatible with each other. Okay? They are not compatible with each other, and they are therefore represented by operators which do not commute with each other. Okay? So, here you have a similar situation. You block the z minus component, let the z plus component go, then send it through a magnet with the magnetic field along the x axis and block the x minus component and let go the x plus component, and if you now let it go through a magnetic field along the z component, you recover this component z minus which you had actually blocked here. Now, this is the very counterintuitive result which I had pointed out, because what comes out of this is Sx plus. So, this is an eigenstate of the magnetic moment along the x axis, but it is not an eigenstate of the magnetic moment along the z axis. Therefore, it is in a superposition state, and you must have the completeness satisfied. So, you therefore have to express it as a superposition of the z minus and z plus, and sure enough, if you send it through a Stern-Gilreich experiment which has got a magnetic field along the z axis, you get both the components. So, it is so beautiful, so correct and so consistent. Do you get it? Yeah, it is confusing. What is confusing is, what makes it confusing is that this is the non-classical result. There is no classical analog. We try to understand everything in terms of what we know, what I am familiar with from my past experience, and our past experience is based on the physics and mathematics that we have learnt in our high school and undergraduate college and so on, where we do not meet these situations. If you have a bar magnet, okay, and I suspend it in this room, how will it orient itself? In no friction, no nothing, I just leave it alone. Let it find its own orientation. What orientation will it find? It will point in the direction of north. Does it have a magnetic moment? It has got a dipole magnetic moment? Yes. Let us say the magnetic moment of this bar magnet is mu. Is it a vector? Yes, it is a vector. Okay? Now, I take this Cartesian coordinate system, x axis, y axis, z axis. The magnetic field is along this, and I ask, how is the magnetic moment of this bar magnet oriented? You will say that it is oriented along the z axis, right? I will ask you, what is the magnetic moment about the x axis? What is the answer? 0. 3 components, mu x, mu y, mu z. Okay? Now, forget classical magnets. Meet our quantum magnet. From its intrinsic spin angular momentum, this is the quantum magnet, this is not a classical magnet, and because it is coming from its intrinsic angular momentum, the definition of angular momentum in quantum mechanics is not r cross p. This is something that we have not met before. So, you need to interpret this in terms of new things which are coming straight out of quantum theory. And the magnetic moment of the electron, which is proportional to the angular momentum, okay, will also not satisfy the same algebra as the classical magnet did. So, for the classical magnet you can get all the 3 components, mu x, mu y, mu z. But for the quantum magnet you can get only one component, the other 2 will not be known to you. Nature hides it from you.
So, at a time only
one component. Yes. Any one. Right? Only one. Okay? So, if you will come back to this Stern-Gilreich measurement, you have got the z component over here and you have no knowledge about the x components, right. So, what comes out are possibly x minus and x plus, both the components, and what has now come out is guaranteed to be in the x plus component. Having measured it, you have completely lost information about the z component, and therefore, if you send it through a Stern-Gilreich apparatus which has got a magnetic field along Z, since you had lost information about it, what does it mean? It means that both the possibilities are there. And if both the possibilities are there, what comes out of the Stern-Gerlach apparatus is an SZ plus beam and an SZ minus beam. This is amazing. Okay? This is quantum mechanics. This is really amazing. And it is very consistent, it is very beautiful. Okay? So, what the measurement does is it induces a system to collapse into an eigenstate, and the probability with which it will pick a particular eigenstate is given by the square of the modulus of the coefficient in the expansion, and the whole formalism essentially becomes, it requires a probabilistic interpretation. Okay? So, we are of course assuming, because this probability is normalized to 1, so probability is some number between 0 and 1. So, that requires our original states to be normalized, so that the inner product is equal to unity. And notice that statistics is inherent to this. Now, this expression looks as if you have inserted a unit operator here and a unit operator here. Okay? But if this Aj, this ket vector Aj is an eigenstate of A, then the relation becomes much simpler. Okay? Because you will have the Kronecker delta popping out, and it will help you contract the double sum over I and j to a single sum. So, successive measurements made one after the other yield the same result, but if they do not yield the same result, it is because the corresponding measurements are not compatible with each other. Okay, some measurements are compatible with each other, and the measurement of x component of the angular momentum is not compatible with the measurement of the z component. So, there is this incompatibility. So, what is quantization? When you say that you have to abandon classical mechanics and you must use quantum mechanics, quantize the system. Quantization means you do not anymore represent the state of a system by q and p, by position and momentum, because they are not simultaneously measurable. So, you dispense with that. Then what do? You represent it by a vector in the Hilbert space, and the measurements of dynamical variables you represent by operators. Once you accommodate this scheme, okay, so this is the mathematical formalism that we are accepting, and the moment you accept it, you have quantized the system. This is quantization. Quantization is accepting a scheme of studying nature. I am not talking about discrete energies and so on. Okay. It is a scheme, it is a mathematical structure which I accept to describe nature. What does this scheme involve? It involves representing the state of the system by a vector and the dynamical properties, dynamical variables as operators. What do these operators do? They operate on the operands, they operate on these vectors, and from this algebra you can develop matrix elements, transition probabilities and other things as we develop the algebra further, and they will connect to our observables. This is what Dirac tells us, that how they connect to our observables will come out very neatly as you develop the algebra further. So, that is what we have undertaken to do. We are developing this algebra further. Okay. So, you can, if you have an operator and you are representing it in an eigenbasis, so that each base vector is an eigenvector of this operator, and now we know what eigenvectors are. They satisfy this eigenvalue equation, right. So, this matrix element of this operator in these eigenstates will give you an orthogonal relationship if the base vectors form an orthonormal basis set. Okay? So, we have seen how statistics enters. Now, this relation looks a little bit complicated, but if you are doing this representation in an eigenbasis, then you get this A operating on Aj gives you Aj times this ket Aj. So, that is the Aj which has come here, and you get the projection of Aj on Ai, which is nothing but the Kronecker delta Ij, and that will help you contract this double sum into a single sum, and you get this result. Okay? So, you have got this probability coming in, right. What you get over here, which is the matrix element of an operator A in the state alpha. So, it is the same state alpha on the right and as on the left, and this is called as an expectation value. Why is it called as an expectation value? Because the measurement can give you any one of the n results. It cannot give you anything else. It can give you only a result which the system may possess. Okay? So, and there are n possible solutions, n possible results. Which one you will get depends on the probability that the measurement will induce the system to collapse into a corresponding eigenstate. So, that is given by this probability, which is Ci square, or in terms of the Dirac notation, it is a modulus square of the component of alpha along the base vector Ai. Okay? And this is like an average value of a quantity. If you carry out a measurement of the height of students in a class, okay, there are like 100 students in the class, and somebody has got a height 1.6 meters, somebody has 1.7 meters and 1.8, 1.5 shorty, okay, a 1.9 a tall guy, a 1.95 an Amitabh Bachchan. Okay. So, there will be all kinds of heights. Now, if you do not carry out a measurement and somebody walks into the classroom and asks you this question, if I measure the height of some student in the class, what do you think the height will turn out to be? It certainly can be 1.9, it certainly can be 1.6, it certainly can be 1.7, right. But very likely it will be the average of all, it will be the arithmetic average of all. The arithmetic average of all of that might turn out to be 1.73, which may not be the height of any of those 100, right. But that is what you will sort of expect. That is what you will expect. That is the reason this is called as an expectation value. It may not be an eigenvalue. It may not be an answer you will get if you actually carried out a measurement. If you actually did carry out a measurement, it will have to be one of the n possible values, because the system can only collapse into an eigenstate. And the probability that if there are many more students whose height is like 1.7, then the chance of getting that as your answer increases. So, that is why this particular eigenvalue is weighted by the corresponding probability. So, it does have a connect with common sense understanding according to our ideas of classical mechanics. In the end, you know, the interpretation will have to be done in terms of what we know from classical mechanics and from our experience, and this is what will take us to the Bohr's correspondence principle and so on. But the whole method of acquiring these results are completely counterintuitive. You can only draw some comfort from Feynman's remark that nobody understands quantum mechanics. Okay, it is a very comforting statement. It is very counterintuitive because it defies our experience. We think that, okay, if I orient a magnet, I will know its x, y and z components. It does not happen in quantum mechanics. Okay. So, this essentially what we have discovered is all the measurements cannot be made. Some measurements are compatible with each other, that you cannot get the x and y both components of a magnetic moment of a quantum particle. Okay. So, these measurements are not compatible with each other. That is an example of measurements which are not compatible. So, what does a physicist want to do? He wants to get as much information about the system as he can. Okay. So, knowing his name is not enough for me, because there may be many others who have the same name. I want to know what is his father's name, which town he came from, right, where was he born, and as much information as I can get. So, this is the complete set of all the information that I can get, but some of this information is not compatible with each other. I will know either this or that. I will not know both. So, that is what is meant by a complete set of compatible observables. Whatever measurements can be carried out which are compatible with each other, so that measurement of one will not disturb the other. It will leave the system in an eigenstate of the other measurement. That alone correspond to compatible measurements. And these compatible measurements are represented by operators in quantum mechanics. This is quantization, and these operators would then commute with each other. So, this is the Dirac's notation, the complete set of commuting operators and complete set of compatible observables, both written as CSCO, is a very nice coincidence. But they bring out two very subtle aspects of quantum mechanics: the idea of compatibility of measurements and the idea of commuting operators. These are completely different things, but they connect to each other one to one. Okay? So, you get information about some measurement, call it A, you ask what else can be measured, and then you get a complete set of compatible observables. The other measurement can be B, then you look for C, you look for D, and so on, as much information as you can get. And all of these measurements will be represented by operators which will commute with each other. Okay? So, we will discuss this further, but before we do that, we need to discuss what is meant by degeneracy, which is what I will do in tomorrow's class. So, I will just introduce what is degeneracy tomorrow, and this is where we will pick up the discussion tomorrow. So, for today, I think I will stop here. The meaning of complete information is not the same as the meaning that you assigned to information in classical mechanics. Your idea of complete information in classical mechanics was that I must know all the three components of angular momentum. Okay, this bar magnet that I was talking about, I should know what is its component along the z axis, what is the component along x axis, and what is the component along y axis, and I can get all the three components, no problem. This is your understanding of complete information. That is not how nature allows you to describe it. Nature says that you can get only one component, and this is complete information. Completeness is to be reinterpreted in terms of what nature allows you to measure. Completeness is not dictated by your prejudice about what you could do using an imperfect theory. You were using an imperfect theory, namely classical mechanics, and you are allowed your understanding of completeness develop on the basis of an imperfect theory. That is not correct. That you can measure only one component is how nature allows you to explore it. And then nature is telling you, this is the complete information. This is as much as you can get, and therefore it is complete. You cannot get any more. Since you cannot get any more, it is complete. It does not agree with your earlier idea of completeness, because your earlier idea of completeness was based on an imperfect theory. So, you connect that and then be comfortable. It does not work that way. Now, this was just the kind of argument which Einstein was raising, that you are missing out that information because some other information is available. You have not been able to access it, but the information is there. All you have to do is to put it in. Okay. So, this was addressed by John Bell. Okay. Now, that is a more subtle part of this story, but since you bring up this point, let me try to share it in a few words. Now, you have got a certain measure of probability in quantum mechanics using this analysis. If you put in this additional information, your analysis of probability will involve this additional information that you want to put in. These are the extensions of your vision. Okay? You can put that in and you will get some estimate of probability. Okay? Nothing wrong with that. That estimate of probability, by putting in this additional information, does not agree with what you find in nature, because if it is the same, then there are certain inequalities which will have to be fulfilled. These are called as Bell's inequalities. Okay, this was a classic work done by John Bell. And what it establishes is that the nature of probability, the nature of uncertainty, the fact that there is some information which nature is hiding from you, is not because your eyes do not cover the entire electromagnetic spectrum, not because some additional information can be put in. David Bohm introduced the idea of hidden variables, that there is something hidden, and if you just put that information, you will get causality and you will dismiss probability from quantum mechanics. Now, the Bell's inequalities, you can work them out and you discover that a formalism based on such a hope is not consistent with observations. It leads to some inconsistencies. These are mathematical inconsistencies. If the lack of information is just because of such a classical set of hidden variables, then you must get a probability which is greater than or equal to something something, but what actually turns out is something else. That inequality is broken. So, that argument does not work.
Putting extra information is completely modifying the system.
Huh?
Putting extra information is.
But it does not work like that. So, we will need to discuss the Bell's inequalities at some point, and we will do it, but perhaps much later.